Section 4.5, uniform circular motion. This is our last section of the chapter, and it's when things aren't just traveling in a straight or even a simple parabolic line, but once you get going in a circle, you can get kind of wound up. So let's take a look, because things change just a bit. So first off, uniform circular motion occurs when you have the particle that's traveling around a circle, or even just around a circular arc. It could be part of a circle. It has to be traveling at a constant speed, so the magnitude of its velocity is constant, but it's constantly pointing in a different direction. So the velocity is constantly changing, even though the speed is the same. Since the velocity is changing, the particle must be accelerating. This is a weird idea. This is depicted here, where the velocity is a tangent line to the path. We have the circular path that's taken. You could imagine this is like a ball on a string. And so at any given point on the ball, you can get the velocity by looking at a tangent line. And the acceleration is what's causing the velocity to change. If there was no acceleration, the ball would just continue in a straight line forever. As it is, the ball is able to keep its same speed, but it gets pulled inward into a new direction so that it's able to stay in this circular path. So our velocity and our acceleration here both have constant magnitude, but a changing direction. The acceleration will also have that fixed value, but it's always, notice, pointing towards the middle, where the velocity is always pointed tangent to the path. So this is a special kind of acceleration. We call this the centripetal acceleration. Centripetal acceleration means center seeking. It's always directed radially inward at any given instant. You can get the magnitude of it with the speed squared divided by the radius r. So v squared over r. This is one of those equations that pops up a frequent amount. It'll pop up even in the future chapters 5 and 6 once we get into circular motion there within forces, because we're going to care about how that acceleration impacts things. So anytime something's traveling in a circle, it needs to have at bare minimum this centripetal acceleration. Another useful thing when you're talking about circular motion is the period of a revolution. So that's the time it takes to go completely around one closed path, one full cycle. And you can calculate that with the period is 2 pi r, right? The circumference of the circle, distance, divided by the speed, v. This is just a rearrangement of v is equal to distance, speed is equal to distance over time. We've swapped out the velocity and the time, and the distance here is just the circumference, 2 pi r. So this is a handy relationship as well. And we can note, if you're not familiar with it yet, it can be handy to note that the period is closely related to the frequency. They're just the inverse of each other. So frequency is when you have some number of cycles per second, or inverse seconds in terms of your units. So it's just the inverse of the period. And that pops up a fair amount as well. So we want to keep aware of that. All right, so with these ideas on uniform circular motion, let's check out a checkpoint. So it says an object moves at a constant speed along a circular path in a horizontal xy plane with the center at the origin. When the object is at x equals -2 meters, its velocity is -4 meters per second j hat. Give the objects A, velocity, and B, acceleration at y equals 2 meters. This is a good one. It's definitely a lot packed into it, so I want you to take some time to think it through, see what you can come up with for parts A and B before you go on. So go ahead and pause your video. All right, did you pause? I'm gonna hope so. So the first thing that we really need here is a picture. That always helps us. So it says it's a circular path, so I'm gonna draw a circle here. And it also mentions it has the center at the origin. So that tells me I could draw on my axes, my x and y. Great. What other information does it give us here? Well, it does mention that when the particle is at x equals -2 meters, the velocity is -4 meters per second j hat. So we can look, there's only one place where it can be -2 and also later be at y is equal to +2, and that's if this is at a distance of 2 meters from the axis. So -2 and +2. Right, and then we can plot this velocity, this negative 4 meters per second j hat. That's the negative y direction. So if I want to draw the velocity in, I could draw it, it's purely in the y direction. And that also clues me in that this has to be on the axis, because that's the only way that we could have a velocity that is vertical, is if it's either at this point or at the other point that crosses the x-axis. All right, so we have that, and it has to be traveling in circles. This tells us it's traveling counterclockwise around said circle. Right, so then we can go at y equals 2, and because we have this great picture and we know it's traveling counterclockwise and that it's moving at a constant speed, that tells us at y equals 2, it's going to be going in the negative x direction, or the negative I hat. And what will its speed be? It's going to be that constant speed, 4 meters per second. So this looks like negative 4 meters per second I hat. Okay, what about for part B? We need to find the acceleration at this point. Well, first off, what's the direction of the acceleration? Remember, the acceleration is centripetal, so it's center seeking. So at y equals 2, it needs to be pointed towards the middle. All right, and then what about the magnitude? Well, that goes back to the centripetal acceleration magnitude is v squared divided by r. So our velocity is, or our magnitude, the speed is 4 meters per second. So we could do 4 squared divided by the radius, which is 2 meters. I'll fill in my units there, meters per second. So we're left with 16 divided by 2. So that comes out to 8 with what units? Meters per second squared. And this just gives us the magnitude of it. So we can take a, we have to fill in the direction. So we say, hey, it's going down. It's going in the negative j hat direction. So we have a negative and a j hat. So this does look like it is, in fact, D. Right, and we could double check this, clear all the drawings and move on. Let's see. And it is C and D. So there we have it. That's an introduction to uniform circular motion. We will be seeing it quite a bit. So I encourage you to lean into the turn, right? And let's go with it. That pulls us through the end of chapter 4.